this problem from a J Advanced 2022 paper. And most of the solutions in the booklet or in the wave is not completely rigorous. I'll try to give you a rigorous solution for this problem. And more importantly, we'll see what's the takeaway in the mindset of question setter. So first, let's understand the question. We have a non-zero complex number z, just because z is appearing in the denominator, such that z bar square plus 1 by z square is having both real and imaginary part to be integer. Okay, so this complex number has both real and imaginary part as integers. Then we have to see the possible value of mod z among the following options. Now this question clearly seems more of a real number theory than of complex number, because the information given is, although is strong, but it feels minimum information. So might be there is infinite possibilities for mod z, at least in the beginning of seeing the question. And you can see all of a sudden these options comes out of blues. So clearly one of the way of striking the question when we have something to be proven to be purely real or purely imaginary, z equals z bar if z is purely real. But that kind of mechanism is not going to help us. So it's not an easy characterization of the inequality to it. Maybe the question is definitely going on the, like hanging on the fabric of number theory. So one of the obvious idea, so maybe the sketch of the solution will be, if someone one of the obvious sketch of the solution will be if someone thinks naturally of putting x plus iy, he'll run into a very, like traumatic calculation, because the expression evaluates to z bar square plus 1 over z square, which gives you x square plus y square whole square. Z bar is mod z square plus 1 by z square, which will be x square minus y square plus 2yxy. So clearly if you rationalize this, x to the power 4 is going to hit x square minus y square whole square. So it will create some x to the power 4 will strike with the still x to the power 4, so x to the power 8. So basically we expect mod z, which is x square plus y square to the power 8, to be mod z should be to the power 4 or something should turn out in xy format. And that options is clearly indicating like we have all options in terms of 1 by 4. Clearly x plus y method is not a judicious way of going about it. So we'll convert this problem and immediately change our strategy to method 2, which is the polar representation of Euler's form. So let's keep z as r e to the power I theta mod z 4 plus 1 by z square, which can be simply cast in the fashion of r4 plus 1 over r square and e to the power 2 theta I sine 2 theta. And now 1 by this is going to e to the power minus 2 theta, which amounts to cos 2 theta minus I sine 2 theta. And now I want this to be equals some integer alpha plus I beta. Alpha and beta is some integer. So by equating, we'll get a fairly simple result, which is r4 plus 1 by over r square cos 2 theta equals alpha, and equating the imaginary part, r4 plus 1 by r square into sine 2 theta equals beta. Now obviously we are asked to find the possibilities for mod z, which is possibilities for r. So it's natural to eliminate theta in the picture. So what we are getting is we'll square and add. So r4 plus 1 the r whole square cos square theta plus sin square theta, that's going to be 1. So that equals alpha square plus beta square. So this is what by eliminating. And if we'll write this, r square plus 1 by r square whole square equals alpha. This guy is already an integer. Hence, we want to find definitely the value of r such that r4 plus 1 by r4 is forced to be an integer. So one thing we can do is we can just try options 1 by 1 and decide for which of them this condition holds. And the number now, since RHS is an integer, because alpha and beta is integer, so r4 plus 1 by r4 is forced to be integer. Now we are lucky because the options we can just go 1 by 1 and screen through the options, because mod z, which is r value in the options, is already something to power 1 by 4. So r4 is going to be nice number. So let's see for the first option. If I going on checking, So 1 by R4 is basically 2 by 43 plus 3 root 205, which let's rationalize. 43 minus 2 root 3 root 205 over is 43 square minus 9 into 205, and a small calculation is there, so which will give you 2 times 43 minus 3 root 205, 43 square, that will be 1849 minus 5 4 and 9 to 18, which gives you 43 minus 3 times 2 root 205 by 2. So this is your 1 by R4 value, and R4 value is already known to us, which is 43 plus 3 root 205 by 2. So 43 plus 3 root 205 by 2. So if you add it, we are having R4 by 1 by R4. 3 root 205 will cancel, and we have, this is 43. 43 into 2 by 2, right? Now, which is definitely an integer. So option 1 is correct according to the given options. You can similarly try for the other options, which is definitely easier to do this. And let me try for option B, where R4 is 7 plus root 3 by 4. So R4 is 7 plus root 3 by 4, and 1 by R4 is 4 by 7 plus root 3, multiply with 7 minus root 3, and it's going to give you 49 minus 3. 49 minus 3 is 46, and clearly you can see R4 plus 1 by R4 is not going to be integer, right? So it's not integer, so that makes option B wrong. And similarly we can just check for the other options. That will give you 9 by 2 and 7 by 6, which is not an integer. Okay, this calculation you can do. I think you'll get 9 by 2 or 7 by 2. 7 by 2 perhaps you'll get from here. So that's still not an integer. So that's the end of the problem. And it's fairly straightforward if you connect this with the idea of, like polar format. So there was nothing genius in creating the problem apart from creating the options. Now, the more mathematically rigorous part of the question is, in the solution that I have just discussed, the integer condition for R4 plus 1 by R4 is a necessary condition for existence of complex number, right? So because RHS is integer, so R4 plus 1 by R4 must be an integer. But we have not checked its sufficiency. Like, we did not prove whether it's sufficient or not. So how am I sure, like, if R4 plus 1 by R4 is an integer, under that condition the R that I am getting will satisfy the initial like condition of the problem? Maybe the R that we are getting is unfortunately not satisfying this. Under that case, option A might become a wrong option, and the question will be absolutely wrong, like in terms of the setting. So basically, of course, you don't have to do this much in the examination hall, but at least while doing this problem at home or when you're doing it in an institute, care should be taken to understand and to get the full feel of the questions. So let's try to give sufficient conditions, like is the condition R4 plus 1 by R4 equals integer is forcing it to be in option 1 whether we are getting a particular complex number for this solution to exist. So the value of R that we are getting is, in the right condition, we got 43 plus 3 205 by 2 to the power 1 by 4, right? So this is the value of R that we got. Since I have kept Z equals R e to the power I theta form, so under what condition we got this value? You can clearly see for R4 plus 1 by R4 to be 43. Okay, R4 plus 1 by R4 to be 43. Clearly, what is the value of cos 2 theta and sin 2 theta, right? So if we'll divide this equation, we'll get 10 2 theta equals beta by alpha, right? Beta by alpha. Now from the first options, as we have seen, like beta by alpha value is going to be, just we can compare for the integers beta and alpha. So because we have r4 plus 1 by r4 value as 43, so now we want 43 to be written as, 43 should be written as alpha square plus beta square minus 2, which imply alpha square plus beta square equal to 45. So thus there exists integers such that their sum of squares is 45. So you can give a try. Right. So clearly alpha, if I'll take 3 square plus 6 square is gonna 45. We'll have minus 3 square plus 6 square 45. We'll have 3 square plus minus 6 square 45, or minus 3 square minus 6 square 45, or 6 comma 3 45. So basically we have with 3 and 6 we have got 4 options, plus minus plus minus, and with 6 and 3 we have got 4 options, plus minus plus minus. Okay, so in fact the existence of complex number fortunately is guaranteed here, because 10 to theta is going to be, it's 6 by 3 if I take up one case, which gives 2. So we know theta is going to be half times 10 inverse 2. So now we have a complex number where r is given by this expression and theta is given by half 10 inverse 2. So clearly there exists a complex number for which the both, the y coordinate and the x coordinate is bound to be an integer. So both these heights are integers. So that itself shows the sufficiency of this question. But in general, usually this is an excellent problem, okay, on the complex number, which requires very unusual thinking. The repetition work in testing the integrality of these expressions and options, this is a challenging part which is involved in reducing the problem to testing that integer condition. But proving the necessary and sufficient condition would have been a perfect full length question for JEE in the past years, when probably the paper setters were having, the power to discrete and allocate different marks according to the degree of difficulty of the problem. It's unfortunate, like in the present JEE scenario, because of the compulsion of, taking things, it's unfortunate because of the compulsion of the marks scheme, which is already predetermined. Sadly, the JEE question setters or the team has not much degree of freedom in playing with the problems, at least in terms of concepts. Rather, what they do is basically they combine simple problems, and worn out problems are often clubbed together to unnecessarily create a hype in the problem. Anyway, so with due respect to the problems, the takeaway is very clear. Like, not only conceptually you have to be strong in solving these JEE problems, but also you have to be smart enough in segregating it. So more than a mathematician, you must have a smart engineering brain to tackle these kind of examinations. I hope you must have enjoyed it and understood the depth and length of the problems. We'll come with more interesting problem like this in subsequent lectures.